So now we're going to go through and try to find the maximum values in a three-dimensional sort of function. And we haven't looked at necessarily one of these yet. So we have our fxyz is equal to x squared plus y squared plus z squared. And we have the constraint x4, y4, z4 equals 1. All right, now, we're going to use Lagrange multipliers. All right, although clearly we could solve for z and back substitute it back into f. It might get a little bit tough to do it that way. All right, so define f very easily as this function. G of xyz is going to be x4, y4, z4. Plus, 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 not comma. All right, and from there, remember we have our formula that we're going to take each of the partials for Lagrange. And so f sub x, really easy to find, that's just 2x, is going to be equal to the derivative of lambda g sub x. And lambda gx, derivative of x to the fourth, is going to be 4x cubed lambda. And we can do the same thing with fy and fz. So derivative of f with respect to y and z respectively are going to be 2y and 2z. And derivative of g with respect to y and z respectively are going to be 4y cubed lambda and 4z cubed lambda. All right, and so the question at this point is, what relationship exists? Okay, well, one thing that we could do is we could just divide the sides on each of these by 2x, 2y, and 2z, and we could kind of tailor our system a little bit to the fact that 1, 1, 1 is going to be equal to, if we divide this by 2x, we divide this by 2y and 2z, then we can say that 1 is going to be equal to 2x squared lambda, which is going to be equal to 2y squared lambda. Which is going to be equal to 2z squared lambda. All right, and since they're all equal to 1, well, we could set each of these equal to one another. So 2x squared lambda equals 2y squared lambda, which equals 2z squared lambda. Or, if we divide each of those, we could just simplify that a little bit and say that x squared equals y squared equals z squared. All right, that's pretty cool because we could just substitute that, and if we just wanted to, we could substitute back in for x into the constraint equation and very easily get a solution for this. All right, so, and I think it's pretty obvious in this case that we can suggest that x equals y equals z. All right, so if we substitute back into the constraint equation, then we're only going to get two possible values. So we're going to get that, remember, x4 plus y4 plus z4 is going to be equal to 1, or x4 plus x4 plus x4 is equal to 1, or x to the fourth equals 1/3, since we would get 3x to the fourth. And if we take the fourth root of that, a couple ways to write that. X can be equal to plus or minus fourth root of 1/3, or x can be equal to plus or minus 1 over fourth root of 3. And consequently, z and y are also equal to that value. All right, so that's our optimal values. All right, pretty tough to see that, but that's what we have. All right, that might be pretty difficult to guess from this given equation. Of course, we need to figure out which one's the max and which one's the min, and not surprisingly, because the original function is all quadratics, given this constraint, it's going to be a maximum on that because they're all going to be positive. The only possible minimum would be 0 on this thing. All right, so the min is obvious. That would be f at 0, 0, 0, which is obviously 0. All right, that's pretty easy to see, and that's only because it's quadratic. All right, but so f at plus minus 1 over 4th root of 3 plus minus 1 over 4th root of 3 plus minus 1 over 4th root of 3 is going to be equal to plus minus 1 over 4th root of 3 square plus 1 over 4th root of 3 square plus minus, and then plus, not surprisingly, plus minus 1 over 4th root of 3 square. All right, and what does that simplify into? Well, when we square the plus minus, that just becomes positive. If we square 1 over 4th root of 3, that just becomes 1 over square root of 3, right? Because remember, that's going to be 3 to the 1/4, and if we square that, that's going to be 3 to the 2/4 or 3 to the half. So that's 1 over root 3 plus 1 over root 3 plus 1 over root 3, which is the same thing as 3 over root 3. If we rationalized it, that would be 3 roots of 3 over 3, or the square root of 3. All right, so the square root of 3 is going to be the optimal value on that curve. All right, so a pretty cool example in 3 dimensions to be able to optimize given this constraint. Now let's take a look at a couple problems that we might have seen a little bit earlier with the critical value method. And this is one of them that's actually going to turn into an extremely easy problem. You might remember that we found 3 positive numbers. Sum was 100, product was a maximum. And you might remember, I believe we got 100/3 for each of those. All right, so let's give you the answer. Don't expect that too often, but it was 100/3. You might remember that we had a maximum that was equal to the sum, the product of x, y, z. So let's call that the function that we're trying to optimize. We also had a secondary equation of x plus y plus z was 100. Okay, and this time what we can say is that our function g is going to be x plus y plus z. Right. Now what we can do is we can use that trick of the Lagrange multipliers, and we could set fx equal to lambda g, x, etc. So f sub x is going to be x or yz, and then g sub x lambda is going to be equal to 1 lambda, right? Because derivative of x is 1, so this is going to be 1 lambda or just lambda. So we have yz equals lambda. Right? Fy. Right? Well, if we take the derivative, that's going to be xz. And if we take the derivative of g with respect to y, that's another lambda. All right, so that's good. And then finally, f sub z is xy, which is equal to lambda, which is equal to gz lambda. So what's the relationship that we have? Well, since all 3 of these are equal to lambda, all 3 are equal to one another. And what we could do is, very easily, we could just say these 2 are equal to one another. So yz is equal to xz, which clearly indicates that x is equal to y. So let's hold on to that. We could also set these 2 equal to one another. And so we could say that xz is equal to xy, which would also imply that z equals y. And by transitivity, since x equals y and z equals y, that means x equals z. So we get this relationship, x equals y equals z. We can go back up. We can substitute right here. So we get that x plus x plus x, and remember we had x plus y plus z, was equal to 100. So we have x plus x equals 100, and we can clearly see that x is 100/3. And that also means that y and z are 100/3 as well. And you might remember we did this problem using the critical value method. And the critical value method took probably about 5-10 minutes to be able to do that. I just looked at the time of this. This one took us about 3 minutes to do. So this is an instance where Lagrange multipliers are highly effective to be able to find these sorts of optimal values. All right, so now that we've taken a look at 2 examples in 3 variables, we're just going to take a look at 2 final examples of Lagrange multipliers.